Here we're going to examine the spanning tree election process. The goal of spanning tree is to eliminate layer 2 switching loops. So if we look at this topology, we want redundant links. Right? So if something goes down, or one link goes down, we can bring another one up. However, having loops in our topology can cause broadcast storms, causing packets to loop around in these. So a packet can start here and loop through and loop back down and keep going, never reaching its destination, eating up all our bandwidth, consuming our CPU, things like that. So what spanning tree wants to do then, or what its job is to break these loops somewhere. And it does that by going through various selection processes to determine amongst all of these active interfaces which ones will be blocking or which ones won't be forwarding traffic. So we'll go ahead and look at that briefly. The first thing it has to do, the first election that happens, is it has to elect the root bridge. It's going to be the root of the tree. It'll be the focus or reference point for all the rest of the decisions. The root bridge, or the switch that will be root, is the one with the lowest bridge ID. Bridge ID equals a priority that's configurable and a MAC address. Default priority is 32.768, so if we leave them all the switches in our topology at the default priority, then what really happens is we look at the lowest MAC address, right? I mean, we're still looking at the bridge ID, but if the first part of the bridge ID is the same everywhere, then we end up looking at the MAC address. Next, it has to elect root ports. Root ports are the ports is a port on the non-root bridge with the lowest cost to the root. Cost is based upon bandwidth. So we look first at the lowest cost to the root bridge based upon the bandwidth. Then we look at the lowest neighboring bridge ID. So if we have two paths to the root bridge that are the same, the cost is the same, then we look at the lowest neighbor bridge ID. And last, for a tiebreaker, if those are the same, so we're going to the same bridge, then we look at the lowest neighbor port ID, which is a priority plus the port number. After the root bridge and the root ports have been elected, we have to elect the designated ports. There'll be one designated port per segment, and by default, all interfaces on the root bridge are designated ports, which makes sense because designated ports are the interfaces that have the lowest cost to the root bridge. So obviously the ones directly connected are going to have a cost of 0. Then next we're going to look at the lowest neighbor bridge ID again and the lowest neighbor port ID. Let's go ahead and we'll first look at some default cost values and look at the actual operation and see hopefully that it turns out the way it's supposed to, right? Some of the default costs, we have path cost based upon the original 16-bit standard, also called short. And most platforms will default to the short spanning tree path cost method. There was 802.1t that defined a path cost in the range of 1 to 200 million or whatever, but it's a 32-bit, so we have the original standard is 16-bit, or the short standard is 16-bit, and the long standard is 32-bit. So you can go ahead and check which method your switch is using by using the command show spanning-tree path cost method. So if we want to see that, and we'll do that when we go ahead and get our bridge IDs when we do our example. So some of the defaults, 10 megabits per second is the default cost is 100. 100 megabits per second is 19. 1 gigabit, which is what our links will be, the default cost is 4, and 10 gigabits it's 2 using this method. So let's go ahead and see how it turns out and see if we can figure out which of our switches in a topology will be the root bridge, which interfaces will be root ports, and which interfaces will be designated ports, and lastly the rest will be blocking. So this is the topology we have here. We have 4 switches interconnected and then cross, and then obviously we have these cross links here. So you can see if I didn't have these cross links, then I'd have a nice little, we wouldn't have any loops, but with these cross links we create loops in our switching network. Whoop. So let's go ahead then and find out what our MAC addresses are. We wouldn't necessarily always do this in our network, but right here we're looking at a demonstration. We're trying to see if we can figure out how this selection process is happening. So we're going to go ahead and go on our switches and see what their MAC addresses are, and then I'll come back and write them on here for you so we can start going through the process. First switch, switch 1, do a show spanning tree. And the bridge ID is the priority, which we left at default, plus the extended system ID, which for Cisco is VLAN. So I only have VLAN 1 on here, so this is just an example. So the actual priority is the default of 32.768 plus the extended system ID of 1 for VLAN 1. Since they're all going to be the same, because all 4 of my switches are in VLAN 1, and I've left all 4 of the priorities at the default, we're going to focus on our MAC address and go ahead and I'm going to write those down. So for switch 1, it's FA163EB8 B745. Let's go ahead and go into switch 2. Switch 2's MAC address is FA163EB or 3E9B C7D7. And switch 3. Whoops. We're going to let this error out. We'll just go over to switch 4 real quick. Here. Because I typed EM instead of EN, so it's going to try to translate it. All right, we let it do its thing. EN, show spanning tree. Get this out of the way. Here the address is FA16.3E91.E101. And lastly, switch 4. FA16 3E1D AA00. Something else I'll show you. Let's go back. We'll go back to switch 1. Remember I said earlier you could see which method, which path cost method your switch was using, and most of them will default to short by doing a show spanning tree path cost method. Spanning tree default path cost method used here is short. So just something to know. Short means it's the original 16-bit standard versus long, which is a 32-bit standard for deciding path cost. Now let's go ahead and we'll go back to our PowerPoint and our slides, sorry, and go ahead and write in our MAC addresses. So what did I say the first one was? Actually, you know what? Let me pause for a second. I'll write them all in on the picture, and then I'll come back to it, instead of you guys having to wait for me to do that. All right, I have them written in now. Let's go ahead and look at them. First election process, right? The first thing that happens in the process is we have to elect the root bridge. It's based upon the lowest MAC address. So we look at all of them. They all start with FA16 3E. Okay, this one is 3EB. 9. 9 is less than B. Remember, B is 11 in hex. So 9 so far is going to say I'm the root bridge. Then we look over 3E9. They're both 9s. 1 is lower than B. So this guy, oh, I'm the root bridge. Now we got to go back and we say FA163E1. Okay, 3E1 versus 3E9. This is the lowest MAC address amongst the 4. So he will become the root bridge. He's going to be our reference point for the rest of the tree. Now let's go ahead and elect our root ports. Remember, the root ports is an interface on a non-root bridge that has the lowest path cost to the root bridge. So on switch 3 here, gig 02 goes directly to switch 1 versus 1 going across this link. Remember, based upon our default costs, that each of these links have a cost of 4 because they're all gigabit and we're using the short method. So this guy here becomes the root bridge, or the root port, sorry, on switch 3. So we'll write that in. Now let's go ahead, and there's only one root port on the switch, so we go to the next switch. We find the switch, or the port, or the interface, sorry, with the lowest path cost to the root bridge. Again, we go here, go through here, and then here, the path cost is going to be greater than if we go this way. So this guy here becomes the root on this switch. Go down to this switch. We have two interfaces. One goes up through switch 2 and then down to switch 4. The other one goes up to switch 3 and down to switch 4. Right? Those both have the same path cost. 4 plus 4, and 4 for this link plus 4 for this link. So now what's the tiebreaker? Lowest neighbor bridge ID. If he goes up this one, the neighbor's bridge ID is going to be the priority plus the MAC address, which is FA16 3E9B versus 3E91. This is the lower neighbor bridge ID, which will make port 2 on switch 1, port 2 on switch 1 our root port. Right, so now all of our roots have been elected, correct? If I take a moment to look at it, each switch has a root. Now let's go ahead and elect our designated ports. Remember the first thing, okay, lowest path cost. All interfaces on a root bridge are designated, so we can go ahead right away and just signify that these are all the designated, or these interfaces are designated. Now we only need one designated link, or one designated interface per link. So this one's been elected already, we're good. This one's been elected. Now we just have to go ahead and figure out what our designated is on this one, what our designated port is on this link, and what our designated port is on this link. So let's go ahead and go to switch 3, lowest path cost to the root bridge. So between these two, on this link, again, they both actually have the same path cost, right? 2 goes through 3 and down here, 1 goes down there. Next interesting thing is they actually both have the same upstream neighbor, right? So then that's going to be, so when we say the next election process is the lowest bridge ID, in this case, they're going to be the same. I'm going to get rid of some of these lines to clean some things up a little bit. So what we discovered, we're trying to figure out which of these interfaces will end up being designated. They have the same path cost, right? 1 through there, 2 through there. So the next tiebreaker, as we said, was the bridge ID, lowest bridge, neighboring bridge ID. Well, they have the same neighboring bridge ID also. So the next one, the next tiebreaker is interface ID. And since we'll be able to break it there, because if you have the same bridge ID, it's the same device, and we don't have two interfaces labeled exactly the same. So next then is lowest neighboring port ID, which here will be gig 1. So this guy here becomes designated. I'm going to clean out my lines again. So far so good. Let's go to the next link that we have to worry about. This link here, this one here is already the root. By default, we almost know this is designated, but he does have a lower path. He does have a low path cost, and he does have a lower one than this guy over here in this link, right? Because this guy would go up this way and through. He's just going to go here. So we'll make him the designated on that link. We'll go over here. We We have to elect a designated port on this link. So we go this way, and we go this way. This one will have a path cost of 4. This one's going to have a path cost of 8 because it'll go 4 and then 4 to get to here. So this guy here becomes designated. And if we go through and look and see what's left, this port will end up being blocking because now we have, I should just verify through. We've elected all of our routes. We have, there's a designated port on every link, right? One, this link it's this guy, this link it's here, this link it's here, and this link is the root bridge again. So we have elected all of our route, we've elected our root bridge, our root ports, and all our designated ports. All interfaces that are left are blocking. So GI02 on switch 2 should be blocking, and gig 01 on switch 1 should be blocking, thereby breaking our bridging loops, or our layer 2 loops. Let's just go back and verify that that's what actually happened. Switch 1, we said 1 would be blocking and 2 would be root. 1 is blocking, and 2 is root and forwarding. You notice to see the alternate here, that will help us, it will signify to us that we're using rapid spanning tree, and if we look, other than the fact that it says spanning tree enabled protocol RSTP, rapid spanning tree, you'll notice that when you go through your readings. I know what I should have done, I should have looked at switch 4 first to make sure that he became the root bridge, right? And he did. It even says this is the root bridge. There's two ways you can tell. It says this bridge is the root. That one's pretty obvious. Or you have the root ID section here. The address of the root bridge is right there. It matches the bridge ID of this switch. And so then he is the root bridge, which means his interfaces are all designated and forwarding. So switch 1 and switch 4 we got correct. Switch 2, what do we say for switch 2? That 1 would be designated, 3 would be root, and 2 would be blocking. So show 1 is designated and forwarding, 2 is blocking, and 3 is the root. So far so good. We have followed the election process and predicted where spanning tree would break the loops correctly so far. We look at switch 3, the designated port, as we said it was in our drawing, is port 1. The root is 2, and it is correctly, and 3 was designated. So it looks like we went through the process and the actual switches did what we predicted or said that they would do. So I hope this helped you understand the spanning tree election process a little bit better.